Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on organic reactions, functional groups, polymers and isomerism. And this is for the OCR Salters specification for the polymers and life topic, or the PL topic. So this video is dedicated for all those who are studying A-level and studying this exam board. It has all been built around the specification, so it's not generic like you might find online on some resources where they're quite generic and they tell you information about certain areas of chemistry, but they may not be relevant to you. And so this video is actually dedicated, like I say, specifically for you. And in fact, there's a whole range of these videos, OCR Salters videos. There's year 1 and there's year 2 revision videos like this, the ones with the black screens behind. There's also some whiteboard tutorials which are generic, so I do have some generic content on there which go through specific areas of chemistry that may be of use to you, but these are the ones which are specific to you. So all I ask is that you hit the subscribe button. They'll be absolutely fantastic. They're all for free and I will keep them free as long as people keep subscribing and watching them. Then I'll keep making them. So yeah, just hit the subscribe button. They'll be absolutely fantastic. These videos as well are built up from slides that I've made, so revision slides. If you'd like to have your own copy, you can purchase them from the link in the description box below. They're great value for money. You can use them on your smartphone or on your tablet. You can use them on the move and scroll through them at your leisure. And also I've known people to print them off as well and annotate the sides of the slides. And use them as part of their revision notes. So there's a lot of information on there, but just go and have a look on Allery Chemistry YouTube channel. There's plenty of information on there. Remember to hit the subscribe button as well to get all your updates. So this is looking at OCR Salters, like I say, so it's dedicated to this particular exam board, and we're going to be looking at areas such as acid-base equilibria. So we're going to be looking at reactions of acids with metals and carbonates, for example. We're going to be looking at some functional groups as well, some organic functional groups. We're also going to be looking at some organic reactions such as acid chlorides. We're then going to look at polymers, and then we're going to also look at isomerism. Well, we're actually going to start with isomerism, look at optical isomerism, and looking at how you can spot chiral centers. So this is the video is going to be all on these areas of the topics, and like I say, it meets these specification points. There are 2 other videos as well in the PL topic that kind of make up the full module, but I've broken it down into three videos because it just, you can kind of chunk them into similar formats. But there are 2 other videos to complete this full one, so this is not everything that you'll see. That's why it starts with H at the top there, because all the other points are covered in other videos. Okay, so let's start with optical isomerism first. You can see a picture of my hands there. So optical isomerism, I'll show you what they mean in a minute. It's not a mistake. Okay, so optical isomerism is actually a form of stereoisomerism, which means they have the same structural formula. So these molecules have the same structural formula, but they have a different arrangement of atoms in space. Okay, so this is what we mean when we say something is an optical isomerism. And effectively, optical isomers are mirror images of each other, and they have a chiral carbon atom. And we'll look at how you can spot. We'll look at spotting a chiral carbon atom in the next slide. But a chiral carbon atom is effectively something where you have 4 different groups attached to the carbon atom, okay, right in the middle. So that's what makes something chiral. And if it has that, if you have a carbon with 4 different groups coming off it, then you can have optical isomers. And effectively, we can arrange these groups, so the carbon with the 4 different groups, we can arrange it in 2 different ways. And we call this enantiomers. So you can get the effectively mirror images of each other. And so we'll look at that in a moment. So, like I say, the mirror images, they're non-superimposable. No matter which way you actually turn them or orientate them, they will not overlap. Okay, so hands are a classic example of a chiral center because they're mirror images of each other, but they're non-superimposable. So you can see they're both hands, they both have thumbs, and both hands have a thumb, and they have 4 fingers, as you can see on there. So they are a mirror image of each other, so they're non-superimposable. So to kind of show you what I mean when I say non-superimposable, I think it's easier to show you in a diagram. I think I made a very short video. It's a blockbuster, this one. So I made a short video just showing you basically how something's chiral. So just have a quick look. So you can see when I move my hands over the top of each other, they don't overlap. So I'll do it again. I'll click it again. So if you see, it's a mirror image. Okay, so there's your mirror image there. So if we draw a mirror line down, they're mirror images of each other. But if I move them on top of each other, and no matter which way around I turn it, it's not going to completely overlap the hand underneath. So let's have a look. So there we are. Okay, so you can see it doesn't matter which way I turn it, it's never going to overlap. And this is what molecules are. They are chiral as well. Okay, so they're mirror images, but they're non-superimposable. But the criteria for something in a molecular level is that you have a carbon in the middle with 4 different groups surrounding it. So you can see the green, the red, the blue, and the brown atoms there surrounding the white carbon atom in the middle. So this is a chiral. These are chiral molecules. And we always have a pair. So we have a mirror image, and these are called enantiomers. Okay, so enantiomers, you have a pair of enantiomers. Okay, so let's see how we find this chiral center, because obviously we know what a chiral center is, we know the criteria, but what we've got to be able to do is find one. Now, the best way of doing this to find a chiral center, or to draw the enantiomers, should I say, is you find the chiral center first. We then draw the 3D tetrahedral shape, which you would have seen in year 1 chemistry, and then we show them as enantiomers. So you can see here, first we need to find the carbon atom with 4 different groups surrounding it. Okay, so you can see there's our molecule there. So see if you can see where there's 4 different groups. Okay, so we've got one here, which is the blue one, and we've got one here, which is the red one. That's your bromine. We've got a yellow hydrogen, and then we've got like an orange yellow, and then we've got a bright yellow carboxyl group. So the chiral center is in the middle. So you can see there we've got 4 different groups surrounding the carbon atom. So this particular setup here is optically active. Okay, so it's a chiral center. So then what we need to do is draw this using a tetrahedral 3D shape. Okay, so it looks a little bit like this. Okay, so that's your 3D shape. So remember, when drawing your 3D molecules, you always have a wedge that's coming towards you that says that this is obviously coming towards you, and then you've got a dotted line going away, and then you've got these 2 that are in the plane of vision. Okay, they're on the carbon atom. Okay, so we then draw our mirror image to show both of our enantiomers. Okay, so we draw a mirror line down, and we draw the mirror images of both of them, and that's effectively how you show that these molecules are chiral. So the first thing is you find a chiral center, you draw your 3D shape, and then we draw them as enantiomers with a mirror line down the middle. Okay, right. So how do we actually detect these? So you can see they've got the same types of carbon, same types of molecules, same molecular mass. They're really difficult to actually detect, but there's one method in which we can use to detect optical isomers, and we use something called plane polarized light. So what we need to know is what is plane polarized light first, and how do optical isomers affect the pathway of plane polarized light. So let's have a look. So optically active isomers, so they're the ones that we've just seen before. They will actually rotate plane polarized light, and this is how we detect optically active compounds. So standard light, so normal white light that comes through the window, like that's like literally towards me now, this standard white light oscillates in all directions, and so I've put all the waves on there showing that they oscillate in various different ways. Now what we can do is, if we place a Polaroid filter in front of that, a Polaroid filter is something, if you do physics you're probably aware of this, but if not, then a Polaroid filter basically blocks some of the oscillations of the light that's coming through, and only lets one plane of light go through. So in this case it's the blue one that's gone through. All the other waves, all the other oscillations have been blocked. Okay, so that's the only one comes through. So there we have made our plane polarized light. Okay, so it only oscillates in one direction. Now you can see in that test tube that we have our optically active compound. So we have a substance in there, and what we're going to do is shine the plane polarized light through that optically active compound. And if it is optically active, if what is in there is optically active, and has a molecule with a chiral center in it, then what it'll do is it'll rotate that plane polarized light. So it'll rotate it right, and it can rotate it left as well. So depending on what enantiomer is in there, will depend on if it rotates right or if it rotates left. Okay, so there we are. So one enantiomer rotates it rotates like clockwise, the other one will rotate it anti-clockwise, and they're also known as D and L. Don't worry about which one's which. You just need to know that one enantiomer will be called D and one enantiomer will be called L. Now, what's interesting here, an important point, is actually, say if you got this enantiomer here and it rotates it clockwise by 5 degrees, this one here will rotate it anti-clockwise, but by the same magnitude. So it's still by 5 degrees, but it's just in the opposite direction, okay? So they'll each rotate the light by the same amount of degrees, it'll just rotate it in opposite directions. And we can obviously label them as D and L, okay? Right, so natural amino acids, you would have, or you will see amino acids within year 2 chemistry in particular. So natural amino acids are mostly L amino acids. So apart from glycine, which you'll see, if you haven't done this topic before, then you'll know that you've got a variety of different types of amino acids, and glycine doesn't have an optically or chiral center because it has a hydrogen where the R group is. But if you haven't done that topic, you might be thinking, what on earth are you talking about? But if you have, then you'll know what I'm talking about. So, and most sugars are D isomers, okay? So you've got L amino acids and D isomers for sugars, okay? Right, so it is possible to have molecules with loads of chiral centers, so you can have more than 2 optical isomers in the same compound. So let's just have a look at an example here. So ascorbic acid is known as vitamin C, and it's found in citrus fruits such as oranges, lemons, limes, etc. It has loads of chiral centers. So what you need to be able to do is look at a molecule like this and be able to spot all the different chiral centers in this molecule. So remember, a chiral center is where you've got a carbon with 4 different functional groups surrounding it. Okay, so we need to look for carbons with 4 different groups attached to it. So let's have a look here. So the first one is there. So this is chiral, as the carbon is immediately bonded to OH, hydrogen, a CH2, and a CHO as well. Okay, so this is bonded to 4 different groups. So it's definitely chiral. So can you see if there's another one? There definitely is another one, by the way, but can you see where it is? Okay, so the other one is actually here. There it is. Okay, so this is chiral, because the carbon here is directly bonded to an oxygen. It's directly bonded to a hydrogen. It's bonded to a COH, which is down here. And it's also bonded to a CHOH, which is up here. So we've got 4 different groups around that carbon atom. So you can see here, this has 2 chiral centers in there. So just be prepared to look out for multiple chiral centers in your molecule. Okay, so let's move on, and we're going to move on to the other part of this topic, which is aldehydes and ketones. So aldehydes and ketones have a carbonyl functional group. So this is C double bond O. Okay, you might have seen this before. So the difference between aldehyde and ketone is just the position of that carbonyl group. So if it's in the middle or is it on the end. So for example, with aldehydes, that carbonyl group is actually sitting on the end carbon, and we end it with al. So we put al on the end. Okay. So you can see here, this is called propanal. Okay. And then you can see here, this one is called ethanal. So this has got obviously 2 carbons, so it's ethanal. This one's got 3, so it's propanal. So we always end it in al, okay, at the end. So we drop the E for propane, and we just put al on the end instead. So that tells you it's an aldehyde. Now a ketone is actually this very similar, except that carbonyl group, that C double bond O, is in one of the middle carbons, and we actually end it in -one. So a classic example would be propanone, which is this one here. You might have longer carbon chains. Then what you have to do is you need to specify where that carbonyl group is. So which carbon does it sit on? So an example here is this one. So this is pentan 2-one. So we're saying that the the carbonyl group is sitting on the 2nd carbon in this 5 carbon chain there. Okay, so as long as you're aware of what an aldehyde and a ketone is, because you're going to come back to these a little bit later on, and you need to know the reactions. So this topic, there's a lot of organic chemistry in this topic actually. So there's a lot of introduction of these different substances and knowing how they react. So there's a lot of this, and you look at the reactions, you know, as we go through. So we're now going to look at a different type of functional group, and this is called a phenol. Okay, now phenols have a hydroxyl group, so they have an OH group, and that's attached to a benzene ring. Okay, now if you haven't seen benzene yet, or you're not sure, you think, well, what on earth is a benzene ring? There is. You will need to know it for year 2 anyway. But a benzene ring is just 6 carbons, and it's got a delocalized electron system in the middle. So it looks a little bit like this. So there's phenol. So you will need to know it eventually. But you can see on here we've got our benzene, and you'll look at it. I'm not quite sure which topic it is in Salters where you actually look at benzene, but you will have there is definitely a topic in there where you look at benzene. You see this delocalized electron system in the middle here with our benzene ring around the side, and you've got OH on the top there. Okay, so this is a phenol. So you can also have this, which is 2-methylphenol. So basically we just added a methyl group there. Now, in terms of the nomenclature, the numbering of it, this one is always going to be carbon 1, which is this one here. This is going to be carbon 2, because this is the second carbon from carbon 1. So we always, when we're numbering phenols, we always call this carbon 1. Okay. So another example, excuse me, is salicylic acid. It's used to make aspirin, this chemical here. So I'm just showing you different varieties of different organic compounds, and obviously you're going to put all these together throughout year 2 chemistry. So this is just a bit of an introduction. So we've looked at aldehydes, ketones, and we know what a phenol is. Okay, so it's just a benzene ring with an OH. So another type of molecule, similar to a phenol, it has an OH group, are diols. So diols are just the same as alcohols, except they are molecules with 2 OH groups that's attached to them instead. Okay, so diols are named by actually counting the carbons on the main stem and assigning a number to which the OH group sits on. So it's exactly the same as numbering functional groups as what you were seeing in halogens and halogenoalkanes or alkyl groups, etc. So we number it in the same way. So let's have a look at an example. So this one is ethane 1,1-diol. Okay, you can see we've got 2 carbons here, and the carbon or the OH groups, the 2 OH groups, because remember it's a diol, so we always have 2 OH groups, are bonded to the same carbon. So that's going to be carbon 1,1,1-diol. Okay, so very similar to how we've seen it before. Let's try it slightly differently. Let's try an isotope of this. So this is this one. So it's ethane 1,2-diol. So this time we've moved one of the alcohol groups to the second carbon. So it's ethane 1,2-diol. Let's look at another example. So this one is butane 2,3-diol. So I think you're getting the idea of how we can actually name these. So very similar to an alcohol, but we just have 2 of them instead. So the di meaning 2, so 2 alcohols. Okay, so we've looked at aldehydes, we've looked at ketones, we've looked at phenols, and we've looked at diols. So now we're going to kind of take it a little step further and look at another type of organic chemical, or organic molecule, which are anhydrides, so acid anhydrides. So acid anhydrides is a molecule that's made from 2 carboxylic acids that could be the same or different. Okay, and the general formula for this is RCO2, CO, and then R. Okay, so these are funny molecules really, but they can be a little bit complicated to spot. I think you just got to look at them really carefully. But acid anhydrides are named by knowing the carboxylic acid it's made from and removing acid and adding anhydride instead on the end. Okay, now this is where it gets a little bit complicated, because if different carboxylic acids are used, then we list the R group in alphabetical order, and if the R groups are the same, we only write the name once. Okay, so this is where it gets a little bit confusing, like I say. But let's have a look at some of the examples. So here's one here. Okay, so you can see that we've got, it looks a little bit like, just before I show you what the answer is for this one, but it looks like 2 carboxylic acids that have been joined together, but we've kind of got this oxygen link here between the 2. But you can clearly see that these 2 are made from 2 different carboxylic acids. So we've got an eth one here and a prop one there. So we have to name it in alphabetical order. So this one's going to be ethanoic, propanoic, anhydride. Okay, so always alphabetical. So it doesn't necessarily mean just because the one at the top is first, you don't name it that way. So it's ethanoic, propanoic, anhydride. Okay, so this is where it gets a little bit confusing, because if we look at this one, This one's got the same length chain for each of the strands here. So you might think, okay, well, this one's eth. You might think that's ethanoic anhydride. It isn't. All we do is we drop the second ethanoic and we just call it ethanoic anhydride. So if they're made from the same length carbon chain, the top and the bottom one, we only have to write the name of the acid that's made it once. So in this case, it's ethanoic anhydride and not ethanoic anhydride. Okay? So just watch out for that. It's a little bit, it's not too complicated, I suppose, but you just got to remember it. Just be wary of that. Okay. Okay, so we've looked at quite a few there, as you can see. So we've looked at loads of different types of new organic molecules that you've seen that you haven't seen yet, which are acid anhydrides. So we know what they are. We know what a phenol is. We know what aldehydes and ketones are. And we know what a diol is as well. So these are all kind of new molecules, and we're going to kind of use some of these later on. You're going to see some of the reactions of these. For example, in polymerization, the benzene one you're going to see in another topic within year 2. So you're not going to see a lot of it in here. You're going to look at some anhydrides as well. So you're going to see how these are used, but we just want to do an introduction of them first. Okay, so what the exam board want you to know is, as you can see, a lot of different functional groups. You need to know all of these functional groups. It's so important. You need to know the general formulas of these as well. You need to know the nomenclature of them. In other words, the prefix or the suffix of all of these functional groups. There's what we're trying to do is basically trying to summarize the functional groups in organic chemistry, which you need to know for AS and A2. So some of these you would have seen from AS and A2. Sorry, I'm in the wrong year, aren't I? AS, so year 1 and year 2. Okay, this AS still exists, but A2 doesn't, so it's just A level. Right, anyway, stop ranting. So, alkanes. C, okay, general formula CnH2n plus 2, pretty straightforward. We have an ane at the end, so alkane, example is propane for an alkane, okay. Another type of functional group is alkenes. You need to know about them. So the general formula, I'll not tell the joke if you've seen any of my other videos. All right, then I will. Why are Geordie's so good at chemistry? Because they're alkene. Yeah. Okay. Next, general formula CnH2n. The prefix of the suffix is ene, and the example is propene. So again, fairly straightforward. You would have seen that. Another one is alcohols and diols, because we've looked at diols now. Okay, we've just been introduced to them just earlier on. So they have an OH group. The general formula is CnH2n plus 1 OH. So that's the general formula for this. The prefix of the suffix, so for alcohols, we use ol or hydroxy, okay? And for diols, we use diol and dihydroxy, okay? An example would be methanol or ethane diol, okay? So depending on what we're looking at there. Okay, so arenes. Arenes, you can see here that we have the benzene molecule there. Arenes, as anything with the benzene in there, we have this group that's just flicking off here. This is the methyl group at the end there. Okay, so the general formula is RC6H5, whatever this could be. This could be an alkyl group, sorry, not a methyl group. Prefix or suffix, phenyl or benzene is how we would name it. An example would be methyl benzene as an example. And obviously phenols, we've seen phenols already, but phenols have that OH group, very similar. They have an OH group except on there, and the suffix is phenol. Okay, so for example, 4-methylphenol is that example on there. Okay, so let's carry on. We need to know a lot. There's a lot of functional groups, as you can see, but it's nice to summarize it. It's nice to pull it all together so you know exactly what you need to know, and there's nothing additional in this. So haloalkanes or halogenoalkanes, as they're also known. General formula CnH2n plus 1 X. X representing halogen. And we always use a prefix for these. So it's either fluoro, chloro, bromo, iodo, any of them. An example is bromopropane. Okay, so bromopropane, chloroethane, whatever it is. Okay, fairly straightforward. Okay, next type are ethers. So ethers have this oxygen sandwich, which is very appetizing. So they've got this oxygen sandwiched between these two R groups here. General formula of an ethane, of an ether, is CnH2n plus 2 O. Now we use the prefix alkoxy for ethers. So for example, you can use methoxymethane as an example. Okay, so another one are amines. Okay, so primary amines are diamines. So general formula is you've got NH for an amine. General formula is CnH2n plus 3n. Prefix, suffix for amines, use amino as a prefix, or sometimes you can use amine at the end as a suffix. And then for diamines, we just use diamino or diamine at the end. So we can use either of them. So an example would be aminopropane or diaminopropane. Okay, so any of them examples there. Okay, so let's carry on. Let's keep carrying on looking at some functional groups. So amides, very similar to an amine, except they have a carbonyl group attached to it. So don't get them confused. So an amine is where you have an NH2 or an NH group, whatever it is. You can get primary, secondary, tertiary ones. But an amide is where we have a carbonyl group that's directly attached to the CnH2, directly attached to the NH2 group here. So the general formula is CnH2n minus 1 ONH2. Wow, there's a lot there. The suffix is amide, so we just put amide on the end. For example, ethanamide. So we'll look at amides later on. There's a little bit you need to know about amides and secondary amides for that matter a little bit later on. So you will see them. Aldehydes we've seen. General formula CnH2nO. Prefix is al, and an example is ethanol for this. Carboxylic acids and dicarboxylic acids. So carboxylic acids have the formula CnH2nO2. The prefix or suffix for carboxylic acids is carboxyl, or it can be oic acid. And for dicarboxylic acids, it can be dicarboxy or dioic acid. And again, you'll see that later when we look at later in the video when we look at polymerization, you'll see dicarboxylic acids later on. So, for example, it would be ethanoic acid or dibutanoic acid. Okay, so we're nearly there. Esters. So esters have this group where you have the C double bond O and an R group at the bottom here. General formula CnH2nO2. The suffix is O8, so it ends in O8. An example is methyl ethanoate. Okay, for esters. Right, okay, so another one, acid chlorides or acyl chlorides, they're also known as. We'll see a little bit more of them as well later on in this video, so you can see a lot of organic chemistry here. General formula CnH2n minus 1. OCl is the general formula. We ended with oil chloride, and an example is methanol chloride in this example here. We've seen anhydrides already, so these are acid anhydrides. So general formula CnH2n minus 2O3. Prefix, suffix, we always have a suffix for this, which is oic anhydride, as you've seen before. So a classic example would be propanoic anhydride. And then finally, our ketones. So ketones have CnH2nO, which is the same as an aldehyde, but obviously with a ketone, the carbonyl group sits in the middle carbon, always ends in -one, and the example is propanone. Okay, so there's a lot of functional groups there. Now, you need to be fully aware of all of these functional groups, and the key thing, I think, when you're looking at an example in an exam is to be able to spot some of these functional groups. And if you can spot a functional group, you can then link it with a reaction and then take it from there. I think the key thing is what the exam board will do, or may do, should I say, is they may give you a large molecule, they probably will, a really horrible, nasty molecule. But it doesn't matter. You're just looking for specific functional groups. And once you know the functional group and you familiarize yourself with them, it's that bit that does all the reacting. All the rest of it doesn't really do a lot. Okay, so don't be too alarmed if they give you a horrendous functional group of some kind of, some anti-malarial drug or some kind of analgesic that's been developed. You look at it and think it's got about 6 benzene rings stuck to it. It doesn't matter. Look for the functional group. So in the next slide, I'm going to give you some of them horrible molecules, and we're going to try and just identify the functional groups. And then once we know what the functional groups are, we can then think, okay, well, what reacts with it? What type of reactions do we have with that? So let's have a look. So you need to spot functional groups in a molecule. So I'm going to give you some of these horrible molecules here, but don't be alarmed, okay? The reason why is to kind of condition you to thinking, okay, well, this is actually not so bad. So this is paracetamol. We know what paracetamol is. It's a painkiller. So see if you can spot the functional groups in this. Okay, so we look at the first one and we can see we've got a phenol there, okay, and we've got one more functional group, which is that one, which is an amide. Okay, so make sure you be able to do that. So I'm going to show you another one, okay, and see if you can work out the functional groups in this. It's a bit trickier, this one. So this is adrenaline. This is what you have in your body when you're frightened, or you do your fright or flight, adrenaline. Okay, so you probably have a lot of that if you go before an exam as well. A lot of this drug that makes you nervous gives you butterflies, okay? So adrenaline. So the first one is phenol, which is this bit here. It has two OH groups. That doesn't matter. It's still a phenol. It's a benzene ring with an OH on it. It's definitely still a phenol. The OH there is an alcohol. And then this last one here is an amine. Okay, not an amide, because there's no carbonyl group there. Okay, it's an amine. So there's three functional groups in that. So any of these reactions can behave. So if you think about, right, what can react with a phenol? What are the properties of a phenol? What's the properties of an alcohol? What can I do with an alcohol? Secondary alcohol. What can I do with, so that secondary alcohol can be turned into a ketone, for example, so we can oxidize it. What can I do with an amine? Do you know what I mean? So we've got loads of these different types of reactions here. Okay, so I've pulled the stops out for this one. So this is ethyl cyanoacrylate, which is basically the active ingredient in superglue. You can see I was being quite creative with this one. So active ingredient in superglue. So can you think where the functional groups are? Okay, so we've got a nitrile there at the end. There it is. And then we've got this functional group. Yes, that is a functional group. So that's an alkenyl, so just an alkene, so double bond. And we've got this. We have an ester as well. So the key thing, you see, doesn't matter what the molecule is. Don't worry about what it is. You might think, oh, that's an active ingredient in superglue, and you might panic and think, well, I've never learned that. It doesn't matter. You don't need to know. I didn't know the formula of ethyl cyanoacrylate. It was in superglue. I wasn't sure. I looked on the back. I went down to the garage and had a look at some chemicals when I was making this, and I'd seen one of them chemicals on there, drew it on there, and looked at the functional group. So it doesn't matter. You don't need to know all of these chemicals. It's just being able to spot functional groups. You need to remember the functional groups, not the molecules. Okay, so let's have a look at another type, and we've seen some already, and in fact you can see here we've got an amine here. So now what we're going to do is we're going to delve a little bit further and look into amines, and then we're going to look at some amides after that, and we're going to see these types of reactions. So these are the next few slides looking at this. So let's look at amines. So amines are derived from ammonia. Okay, they're derived from ammonia molecules, and they all contain a nitrogen atom, as you can see there, where hydrogens are replaced with an organic group. So, for example, it could be an alkyl group that could be replaced with that type of group. So let's have a look. So a primary amine is this. So we've got an alkyl group there. So there's your alkyl group, which is the red R, and then we've got NH2 at the end. So this is definitely a primary amine. So amines have this distinctive smell. They smell of fish. They don't have a nice smell at all. I don't like fish anyway, but I imagine even if you do, and you get this horrible kind of, it smells like, yeah, it doesn't smell nice. I don't like the smell of it anyway. You might do, but it's got this smell of fish, and it acts as a base. Some of these can be quite powerful bases as well. So as they are bases, they turn red litmus paper blue, and this is a positive test for an amine, as if we react it with an acyl chloride, and we'll see acyl chlorides later. It's just another chemical, but when we do this, we actually get white misty fumes of acidic gas, HCl. So if we react this primary amine with an acyl chloride, we get quite a really vigorous reaction. We get white misty fumes. That's a classic sign, that it's definitely an amine, but obviously the litmus paper as well, and that fish smell as well is a classic sign of an amine. But you'll see the acyl chloride reactions later in this video. There's a lot of interlinking within this video. It's difficult to put everything together into one order, but you'll see that a little bit later on in a little bit more detail. Okay, so amines are named by using the word amine, as you've seen just before briefly in one of the cards just before. So using the word amine at the end and dropping the E from the alkane chain, and we keep the E for diamines, which is really complicated. Okay, so let's have a look. So amines are named by counting the carbons on the main stem and assigning a number to which the NH2 group sits on. Okay, so no different to what we'd see, say with a ketone that we'd seen before. You need to assign a number to it if it's sitting on a middle carbon. It's exactly the same, like I say, as number of things like alcohols on alkyl and halogens and ketones, etc. So no difference. So let's have a look at some examples. It's always better to do that, I think. So this one's ethanamine. Okay, so you can see here we've got 2 carbons here, and we've got the amine group here. We don't need to number it here because it can either only be on this carbon or this carbon, and that would just mean it would be always carbon number 1. Okay, so unless of course we've got 2 amines, then we need to actually then number it, which is the next example. There we are. So you can see here we've got a diamine. Then we do need to number it because we need to say where this second amine is actually sitting. So this is ethane 1,2-diamine. Notice we keep the E for diamine, so it's ethane 1,2-diamine, but we drop the E when it's like this, so it's ethanamine. Okay, so be really, really, really careful. Now, when we have other functional groups involved, remember we have to name them alphabetically. So we name them in alphabetical order. So let's have a look. So here we've chucked in a bromine there just for good measure. Now bromine, so this is dibromobutane. So one bromobutane and then 2,3-diamine. Because that's D, the B becomes before the D, then we must label that as bromo first. So 1-bromobutane, 2,3-diamine. Okay, just to show you as an example there. Okay, right. So you've had a bit of an introduction to amines. So we know kind of what they are, and we know how we name them, and we know that we can have diamines as well. And that will come a little bit more prominent when we look at polymers later on. But like we say, amines can act as a base, so we need to understand how amines actually react and how they interact with other chemicals. So amines have a lone pair of electrons, and that allows them to accept a proton, and obviously they act as a base as well. So a proton bonds to an amine via a dative covalent or coordinate bond. Remember, that's where both electrons come from one atom. So in this case, it's going to be nitrogen. Nitrogen has a lone pair of electrons, and both of them electrons are donated to the hydrogen to form, obviously, your amine. So let's have a look here. So you've got your ammonia, which is here. So there's your amine, not ammonia. There's your amine molecule. There's your lone pair of electrons there. It's going to accept the H+, and it's going to form this. And you can see here that we represent a dative covalent or coordinate bond with an arrow. And the arrow is showing where the electrons are coming from and where they've been donated to. Now this bond is weaker than a standard covalent bond, which is this bond here. Okay. So this whole thing's got a positive charge. The reason why it's got a positive charge is because we've added a H+ sign to it. So overall, it is positively charged. Okay. So amines, as they're a base, they react with acids, so HX, we can represent acids as HX, to form a neutral salt, but they don't form any water. So it's not like your traditional acid-base reaction where you might have an acid reacting with a base such as sodium hydroxide and you form salt plus water. With these molecules, you don't. You actually form just a salt. So you can see that amine plus acid will form salt. Okay, so as a derivative, you can also get amides as well. So you've got amines, so amides are kind of similar, but I don't want you to get confused with them. Because remember what I said before, an amide has a carbonyl group right next door to your NH2 group as well. And there's 2 types of amides that you need to know. One is a primary amide, which looks like this. And you can see that we have this NH2 group here, instead of an alcohol group, because it's kind of, it looks like a carboxylic acid, doesn't it? So instead of an OH group here, we have an NH2 group instead. So it's very similar to an amine, except we must have this carbonyl group bonded to the NH2 there. We can also have secondary amides as well, and secondary amides are very similar to amines, except one of the hydrogens has been substituted for an alkyl group. So that's why we call it a secondary amide. So you can see there, primary amide, secondary amide. You need to be able to draw these compounds here, and you need to be able to know, the main difference between the two. Very similar to a carboxylic acid, except they have an NH group instead. Okay, so amides are named by using the word amide at the end, and we drop the E from the alkane chain. Okay, so very similar to amines. Very similar. Okay, so primary amides are named by taking the longest carbon chain and adding amide at the end of it. So let's have a look. So there you go. So we've got propan amide. So you can see here that we've got 3 carbons here. So this is your prop. And we've got a carbonyl group here and obviously our NH2. So this is propan amide. And your secondary amides are named by using the prefix N-alkyl, okay, where the alkyl part is the group directly attached to the nitrogen, okay. So basically what we've done is we say N because we know this signifies that it's an amide, okay, we've got a nitrogen there. And then basically whatever substitute, where there was a hydrogen, whatever group is there that was where there was a hydrogen, you write it here. So you put methyl. So if this was an ethyl group, this would be N-ethyl propanamide. If this was a butyl group, it would be N-butyl propanamide, etc. Definitely propan because we've got our 3 carbons there. So it's propan amide. Okay, so not too traumatic, I hope. Right. So amides can also undergo acidic and basic hydrolysis, okay? So remember, hydrolysis is hydrolysis. Hydro meaning water, lysis meaning to break. So hydrolysis means we're breaking up the molecule, but we're using water to do it. But we can use acidic and basic conditions because this speeds up hydrolysis, so that's why we use it. So primary amides are hydrolyzed by acids to produce a carboxylic acid, remember it's a derivative of that, and ammonium salt. And secondary ones can produce a salt of the primary amine instead of an ammonium salt, so they're very, very similar. So let's have a look at the reactions here. So here we go. We've got our primary amide here. This is a primary one. We're going to react it with water, and it's obviously an acidic solution, okay, because we need water because it's hydrolysis, but the acid's going to help speed this up. So what happens is the NH2 drops off, and we have an OH instead, so there's our carboxylic acid. And then we have ammonium chloride is left over because we have a hydrogen from here, and we have the HCl that's from here. So we have NH4Cl that's produced. So this is our salt here that's produced. So there we are. So your primary amides are hydrolyzed by dilute alkali to produce a salt of the carboxylic acid. Your secondary ones, instead of producing ammonia, they produce an amine instead. So let's have a look. So here we've got our sodium hydroxide solution. We've got our primary amine, and we're going to form our salt. Okay, so it's the salt of the carboxylic acid salt here. So this, in this case, is going to be sodium ethanoate, and then we produce an ammonia as well. Okay, so for your secondary one, you just produce an amine instead of ammonia, depending on what what group was attached to the nitrogen at the time. Okay, so that's fine. So we know what amides are, and we know how to name them, and we know the reactions of them in terms of hydrolysis. Make sure you're familiar with that and what you produce. Okay, depending on, you're producing 2 different products, depending on if it's base hydrolysis or acid hydrolysis. So now, because we've looked at derivatives of carboxylic acids here, we are now going to look at actually carboxylic acids. And we're going to look at a little bit more detail. You probably would have seen these before, more than likely, in year 1 chemistry. But we're just going to kind of extend on this concept from year 1. And we're going to use this to then apply it to new features such as polymerization. So carboxylic acids have the carboxyl group, which is the COOH functional group. This contains both a carbonyl group, which is C double bond O, and a hydroxy group, or hydroxyl group, which is OH. Okay, so the OH group. So carboxylic acids are named by finding the longest carbon chain, and then we add oic acid on the end of it. Okay, so when naming carboxylic acids, the carbon on the carboxyl group is always carbon 1, so that's very, very important. And the carboxyl group will always be at the end of the molecule. We can never have a carboxyl group in a middle carbon. It's always got to be at the end. Okay, and that carbon in the carboxyl group is always carbon 1. So that simplifies it. It means you know exactly what carbon 1 is, and then we can work along the chain to find out the numbers of the other ones. Okay. So ethanoic acid, this is 2 carbons, so it's eth, and it's got 2 carboxylic acid, it's got a carboxylic acid group at the end. So a carboxyl group here, C double bond O, and then you've got your OH as well. So this is a typical sign of a carboxylic acid. So just making it a little bit more complicated. So this one is 4-chloro. So you can see here, this is always carbon 1 here. So it's carbon 1, that's 2, that's 3, so it's 3-hydroxy. And then 4-chloro. Okay, so 4-chloro, 3-hydroxy butanoic acid. So it's just showing you how you can use the number system to name more complicated carboxylic acids. And then another one is benzoic acid. So this is where you've got a benzene molecule, and then you've got your carboxylic acid that comes off the side there, your carboxyl group. So it's just an aromatic carboxyl group. Okay, so just like we can have alcohols and diols, we can also have carboxylic acids and dicarboxylic acids. So that's what we're going to look at now, which are dicarboxylic acids. So dicarboxylic acids have 2 carboxyl groups, so they have 2 COH groups at either end of the molecule. Remember, these must be at the end of the molecule. We can't have carboxylic acid groups or carboxyl groups in the middle. So carboxylic acids are named by finding the longest carbon chain, and then we add dioic acid on the end, and we keep the E at the end of the alkyl chain. So this is the slight difference here. Okay, so you can see I've got ethane dioic acid, so we keep the E here and we just add dioic acid on it. So this one is ethane dioic acid. And then when naming dicarboxylic acids, the carbon on the carboxyl group is always carbon 1, just the same as carboxylic acids, and the rules around other functional groups still apply. So we number with the lowest possible number combination. Okay, so in this example here, this is going to be carbon 1, this one here, and that's going to be 2, 3, 4, 5. Not the other way around. So it's not going to be 1, 2, 3, 4, 5, because that's going to give you a highest number combination. So it's going to be 2-chloro, 3-hydroxy, butane dioic acid for this one. So always number the lowest number combination. So you would have seen that in year 1 chemistry when you're naming molecules and you're numbering them. You've always got to lower the lowest possible number combination. I will get that over eventually. Okay. So carboxylic acids, their properties. Let's look at some of the reactions of these now. So carboxylic acids are weak acids, and they react with carbonates, bases, and metals to form salts such as sodium ethanoate. Okay, so this should be fairly straightforward for you because this is just a basic acid-base reaction. So carboxylic acids are weak acids, which means they dissociate partially to form a H+ ion and a carboxylate ion. Okay. So let's have a look. So we've got our carboxylic acid here. It's in equilibrium. Okay, so we've got a reversible reaction here. It's forming our carboxylate ion, which is this molecule here, and we've got our H+ ion. So you can see it's dissociated. But because it's a weak acid, equilibrium lies well over to the left, lies over to this side. So we don't have much of these. We don't have much of the carboxylate ion or H+ ion. So hence, like I say, it is a weak acid, okay, because it dissociates poorly. So as they're acids, they react with other substances such as metal, base, and carbonate. So you need to know these reactions here, okay, and you need to know how they actually interact. So let's start with our carbonate first. Okay, so when we react an acid, a weak acid with a carbonate, we form a salt plus water plus carbon dioxide. Very, very straightforward. You must remember these reactions here. Okay, you must know they might give you a different compound. They might give you a different carboxylic acid, of course, but it's the same rules. Always produces the salt, water, carbon dioxide. Okay, no change. Don't be put off by big carboxylic acids that they may give you. If there's a carboxylic acid group in that molecule, doesn't matter how big the molecule is, it will react with the carbonate to form the salt, water, and carbon dioxide. Okay, so you're going to see fizzing for this reaction. Okay, so let's do it with a standard base this time. So we don't produce carbon dioxide with a standard base. We just produce salt plus water, as you can see there. So sodium ethanoate in this case, and water. Again, they can give you just a big carboxylic acid. Don't be put off by it. All you're looking for is the carboxylic acid reacting with your base. Okay, and then the final one is it reacting with metal. So metal plus acid will always form salt plus hydrogen gas. Okay, so you've got to know these types of reactions. Again, they could give you a pretty horrendous carboxylic acid, but it doesn't matter. You're just looking for the carboxylic acid group, and it's that that's going to react with your metal, your base, or your carbonate. Okay, right. So just kind of building up on that. So we know the kind of properties and how carboxylic acids react. They will also react with alcohols to form esters. Okay, and we call this esterification. So if we react this carboxylic acid with, or we can use acid anhydrides, which we've just seen before, these can be used to make esters which have this COO group in the middle of it. Okay, so an ester is produced when we react a carboxylic acid with an alcohol and we use a sulfuric acid catalyst. Now you might have done this in the lab at school, or you might have done it in college. So you can normally just do this in beakers, or you may have actually done it using the distillation kit. So you know that esters have this kind of unique smell. You can either have them as sweet, you can have them like pear drops, you can have it like oil of wintergreen, or you can have it like rancid butter. So they've got a variety of different smells. So quite a nice. I like this. These types of reactions, you get nice chemicals from the nice kind of smelling chemicals, and actually used in the food industry as well. But an ester is also produced when an acid anhydride or an acyl chloride, which we've seen just before, being introduced to that, reacts with an alcohol. So any of them can produce an alcohol, produce an ester as well. So let's have a look at the carboxylic acid. So you can see I've color coded it. So your carboxylic acid is blue, and this is reacting with an alcohol, which is yellow. That's going to form your ester plus water, and you can see here that we're using an acid catalyst here, so we're using H plus in the middle there. And likewise we can do exactly the same with an anhydride. So there's our acid anhydride there, reacting with alcohol, but luckily we get an ester and we get carboxylic acid as a product. So you can see again I've color coded it so you can see where the atoms are coming from, where they're going to. Okay, so fairly straightforward. So we know how to form an ester. So we know, what reagents we can use, acid chloride or acid anhydride, and we can use a carboxylic acid. But all of them are reacting with an alcohol. So that's fair enough. But what we've got to be able to do is name the ester as well. So there's a lot of nomenclature in this topic. So esters are named in two sections. The first bit is named from the alcohol used, and the second bit is actually named from the carboxylic acid. So let's have a look at example 1. So here we're going to react ethanol with propanoic acid. Okay, so we've got our ester there. So the first thing we need to do is this part here of the ester is actually formed from the alcohol and is the alkyl group. Okay, so this bit here. In this example, this is ethyl because we've got 2 carbons there. So we name this first when we're naming an ester. The second part, which is the bit in blue, this bit has come from the carboxylic acid. We name this second, and basically what we do is we drop the oic acid bit from it. So this is propanoic acid normally. And instead of putting oic acid, we put O8 at the end. So in this case, it's going to be propanoate, and that goes at the end. So the total, the full name for this ester is then going to be ethyl propanoate. So it's going to be the first 2 carbons are ethyl, and this is going to be propanoate, which is going to be at the end here. Okay. So let's look at another example. So we're going to react ethanol, a little bit more complicated with this one. We're going to react ethanol with 2-methyl propanoic acid. So you can see here that we've got our eth group here, and we've got propanoic acid, but we've got 2-methyl. So this is your propanoic acid, or would have been your propanoic acid. But you can see we've got our methyl group hanging off the second carbon of our carboxylic acid there. So let's go through and name this. So when we name the branches, okay, so when we name the esters, with alkyl branches, we need to number from the carbons in the COC part, okay? So in other words, this is always going to be carbon 1, closest to the oxygen, and this is always going to be carbon 1 here. So this one's going to be 1, 2, and 1, 2, 3, always numbered that way, okay? So the part of the ester formed from the alcohol is named first, and this is called ethyl. Whereas the carboxylic acid bit on this side is named last. So this is 2-methyl propanoate, and it sits on that second carbon, that methyl group. So the full name of this is going to be ethyl 2-methyl propanoate. Okay, so you can see the numbering is quite critical in this one. Okay, excuse me. Okay, So let's look at some more reactions of esters. And so we're going to be looking at ester hydrolysis for this one. So esters can be hydrolyzed. Remember, hydrolyze or hydrolysis, hydro meaning water, lysis meaning to split or to break. So we're splitting using water. However, it can be sped up, like I say, by using an acid or a base. So we're using acid hydrolysis and base hydrolysis. So we need to know these reactions, very similar to what we did with our amides we've seen before. So we're going to do acid hydrolysis first. So here we're going to use a dilute acid to split the ester into its constituent components. So that was carboxylic acid and the alcohol. So we can use sulfuric or hydrochloric acid, and the reaction is conducted under reflux. So let's have a look. So we've got our ester here, and I've color coded it so we can see what's going where. Okay, and we've got our water here, and it's all dissolved in an acidic solution, so it's in equilibrium. So this is going to form our carboxylic acid, which is there, and you can see the OH has come from the water, and then it's going to form our alcohol, and the hydrogen, as you can see, has also come from the water. So because all of this is in equilibrium, if we add more water to this side here, then more product is actually produced. We produce a lot more of this. So equilibrium, it forces equilibrium to the right if we add more water to this reaction here. Okay, so let's have a look at, still sticking with acid hydrolysis, ester hydrolysis, but we're going to look at base hydrolysis. We're going to look at using a base. So here we use a dilute base instead of a dilute acid, and we split an ester into a carboxylate ion and an alcohol. Okay, so it's slightly different products, but we're using sodium hydroxide for this, and it's normally conducted under reflux because we're using volatile substances here, and we don't want to lose them to the atmosphere, so reflux is perfect for that. So let's have a look at the reaction. So you can see here we've got our ester, and we're going to react this with our hydroxide ion, which has come from our base, and we're going to form our carboxylate ion, which is that, and obviously the O has come from the OH, and the hydrogen then goes to reform the alcohol again. Okay, so very important reactions, but you can see they're quite similar. Obviously, you need to know acid and base hydrolysis for amides, and you also need to know them for esters, so it's a similar type of reaction. Okay, so I did say we're going to look at these as well, which are acyl chlorides, or they're also known as acid chlorides as well. And they have this functional group of COCl, and they're derivative of a carboxylic acid, okay, as you'll see soon. So they have the general formula CnH2n minus 1 OCl. Okay, so that's the general formula. You need to know these general formulas because they can give you, molecules with large numbers of carbons and hydrogens. You need to be able to work them out of the formula. So acyl chlorides are named by finding the longest carbon chain, and then we're adding oil chloride in the end. It is exactly the same as what you'd have with carboxylic acid. There's nothing new here. So when naming acyl chlorides, the carbon on the acyl group is always carbon 1, and the acyl group will always be at the end of the molecule, exactly the same as carboxylic acids. Okay, no different here. So an acid chloride looks like this. See, it looks very similar, doesn't it? So instead of an OH group, we have a Cl group instead here. So this is ethanoyl chloride. Okay, so we had oil chloride at the end. Okay, so ethanoyl chloride. So that's the first one. It can get more complicated versions like this. So this is going to be 3,4-dihydroxy. So you can see here we've got 3 and 4, 2-hydroxy. So we've got dihydroxy, 2-methyl butanoyl chloride. So I've really thrown everything at that one. Okay, so just make sure you're aware of how to name these things. Very, very similar to carboxylic acid. So there's nothing massively new there. Okay, so let's carry on, and now we're going to look at their reaction with, or these acid chlorides, and the reaction with alcohols. Okay, and the reactions of them. So we're going to look at the reaction of alcohols first, and there's another reaction that we need to know, which we'll look at next. But acyl chlorides, they react with alcohol and primary amines, which we'll look at next. In each reaction, the chlorine is substituted for either an oxygen or a nitrogen, depending on obviously what we're reacting with. In this case, it's going to be substituted for an oxygen because we're going to be producing an ester, and they are nucleophilic substitution reactions. Okay, so the reaction with alcohol produces esters. So let's have a look. So we've got our acid chloride here, and that's going to react with our alcohols. Remember before when we said how you could form an ester, and one of them was using a carboxylic acid and alcohol, using an acid anhydride and an alcohol, and the last one was using an acid chloride or an acyl chloride with an alcohol. So we're looking at this particular reaction here. So ethanoyl chloride, reacting it with, in this case, methanol, and we're going to form methyl ethanoate, as you can see there. That's our ester, and then we're going to form hydrochloric acid as well. It's a really, really vigorous reaction. You must be done in a fume cupboard, and the main reason why you do it in a fume cupboard is because the HCl gas that's produced is incredibly acidic and toxic. You do not want to be breathing that stuff in. Really vigorous reaction this. The moment you mix these two together, it very exothermic, produces this white misty fumes of hydrogen chloride gas. Okay, so let's have a look at the reaction of acyl chlorides with primary amines. Now, these produce secondary amines, as we'd seen, secondary amides, sorry, as we'd seen before. So there's our acid chloride, and that's going to react with our primary amine, okay, or acyl chloride, should I say, and this is going to form our secondary amide. So remember, when we're naming secondary amides, we put the N in the front there, and the hydrogen here, there was normally, if it was a standard amide, you'd have two hydrogens here. One of the hydrogens has been substituted for this kind of methyl group here. Well, it's not kind of, it is a methyl group. So it's N-methyl ethanamide. That's the total molecule there. We still produce hydrogen chloride gas. It's a very vigorous reaction. White misty fumes are produced. We must do this reaction in a fume cupboard. Okay, so fairly straightforward reactions. You need to know them specific ones. A lot of this is just knowing how you can make things. So I suggest, there's a lot of different reactions here and a lot of different functional groups. Is you just keep practicing. Run through the video again and make sure you're fully aware of everything that's going on. Okay, so now we're going to kind of step away from some of these functional groups here, and we're going to look at a particular kind of niche area of chemistry, which is polymerization and forming polymers. Now, we're going to start with addition polymers first, okay? So addition polymers is where we have alkenes that join together. These are monomers, which are the individual units that they join together to form an addition polymer, okay? So you would have seen this, a reminder of addition polymers from module 4. You would have seen, I think module 4 is a different exam board I think I put in there, but you would have seen addition polymers in year 1. Okay, I'll get that changed. So I think I've just I've been on a different exam board mode there. So to make polypropene, we need the monomer, or we need the monomer propene, and add a few of these together to make polypropene. Okay, so let's have a look. So there's our alkene there. Okay, so this is a monomer unit. Okay, so a monomer is something where it's your standard alkene molecule there. It has a double bond, and what happens is this double bond opens up to form a repeat unit. So let's have a look. So there it is there. So we've opened that double bond up. Now you'll notice two things here. One is the brackets, which suggest that this is a repeat unit with the N, and the N actually tells us how many repeat units we have. And the other thing is these trailing bonds. So this is where we have a number of these repeating along a chain down along the side there. Okay. So like say one repeat unit, so the double bond is not here anymore. And we have these trailing bonds as well that extend beyond the brackets. And so if we join a few of these repeat units together, then we form this. Okay, so this shows a repeat unit of two monomer units that have been joined together. And you can see there that we have this repeating pattern here. So we have this CH3, CH3, and we can keep on repeating that. And that's how you obviously find out what your monomer units are. So polyalkenes are saturated molecules. They're normally non-polar, not great for decomposition because they don't react with anything. So if we put these in landfill, these are the plastics which will sit around for years and years and years and years, and they won't degrade. They won't degrade well. So really, these are the types of plastics that we want to try and stop from going into landfill and recycle them, remelt them down. Do something useful with them. Okay, so they don't degrade well in landfill whatsoever. Saturated means, just before we move on to the condensation polymers, but saturated means that they have no double bonds in them, so they're saturated with hydrogens, as you can see there. Something that's unsaturated will have double bonds in there. Okay, so saturated is commenting on the hydrogens in the chain. In other words, there's no double bonds in there. Okay, so let's look at condensation polymers. So there's two types of polymerization. You've got your addition polymerization, which we've just seen before using alkenes, and then we've got condensation polymerization, which is these types of polymers here. And so they're comprised of two main types. You've got polyamides and polyesters that you need to be aware of. Okay, so condensation polymerization occurs when we have two different monomers and they have at least two different functional groups that react together. Okay, and then we form this link between the two, depending on if it's an amide or an ester link, but we'll have a look at that in a moment. And water is eliminated when we join these two monomers together, and this is why we call them condensation polymerization or condensation polymers, because we always eliminate water. Okay, and like I say, that link is determined by which molecules we actually bond together. Is it going to be a polyamide or an amide link, or is it going to be a polyester with an ester link? So you can see here the types of polymers are polyamides. These are formed by reacting diamines and dicarboxylic acids together, and polyesters are formed by reacting diols and dicarboxylic acids together. Okay. So the key thing here is we've seen diols and dicarboxylic acids, but we need two alcohol groups either side of the monomer, and we need two carboxylic acid groups or two diamine groups either side, or two amine groups either side of the molecule, either side of the monomer molecule to form your polymer. Okay, and you're going to see some examples here. So let's have a look at polyamides first. Okay, so polyamides are actually formed by reacting dicarboxylic acids and diamines together. This is no different to how you would normally form an amide. So an amide is normally where you take a carboxylic acid and an amine together and you form an amide. Okay, so this one is a polyamide, so we need two of each functional group either side. So amide links are formed when these react, and so we have to use dicarboxylic acid and diamines. They've got these functional groups either side because that allows us to form long polymer chains. If we didn't have these two functional groups either side, we wouldn't be forming a long polymer chains. So let's have a look. So we've got our dicarboxylic acid here, very classic, two carboxylic acid groups either side, and then we have our diamine, which is there, so we've got two NH2 groups either side there. So this is going to join this together and we're going to form our polyamide, and there is our amide link in the middle. Remember, an amide is where you've got a carbonyl group, which is here, bonded with an NH group, which is there. So that is definitely an amide link. Now we call this condensation polymerization because we're eliminating water as we're joining these two things together. So this is definitely a condensation reaction. Okay, so let's have a look at a specific example of a polyamide, and we're going to look at nylon 6,6. So nylon 6,6 is a polyamide that's used in ropes and carpets, clothing, parachute fabric. So you kind of get the idea of what it's like. It's very durable, very strong type of fabric here. And nylon 6,6 is actually made from hexane dioic acid and 1,6-diaminohexane. So the 6,6 refers to the number of carbons in the monomer units. So you can see here that we've got hexane dioic acid, which has 6 carbons in there. So there's 4 there and 2 either side there. So that's got 6 in. And then we use 1,6-diaminohexane, which also has 6 carbons in there. So this is where the 6,6 comes from. The two monomer units used to make it have 6 carbons each. And we can join them together, and that forms nylon 6,6. And obviously we have 2 water molecules that have been eliminated as well. And you can see we have our ester link, our amide link in the middle there. Okay, so that's nylon 6,6, but we can also have something called nylon 6,10 as well. And 6,10 is again used in the same type of materials. It's just a similar type of polymer, except 6,10 is made from decanoic acid and 1,6-diaminohexane. So we're making it from something which has 10 carbons in here. So it's one there, and then the 8. So it's decanoic acid. Still a dicarboxylic acid and a diamine. So that's still, that's still the same. It's just we've now got 10 in here instead of 6, what we had before. We've still got 6 in here, so that's fine. And that's going to form nylon 610, which is there. Okay, and then we form 2 water molecules there. So you can see the numbering on the nylon tells us the number of carbons in each monomer unit. Okay, but nylon can also be made from 1 monomer unit instead of the 2, like nylon 66 and nylon 610. So an example would just be nylon 6. Okay, so nylon 6 is made from a monomer with an amine and a carboxylic acid group on each end. So instead of using a dicarboxylic acid and a diamine, we have 1 molecule with an amine and a carboxylic acid at each end, okay, because we must have that for these to form amide links. So here's an example here. So this is nylon 6, and you can see here that nylon 6 has got the monomer unit would have a carboxylic acid at one end and an amine at another end. So you can just use this repeat unit to join and make your polymer. So that's just nylon 6. So just be aware of that you don't necessarily need 2 different monomers to form nylon. Okay, so nylon is quite versatile. So just kind of how do we apply this then? So nylon has the following general formula. So you need to know a lot about these general formulas. So if made from 2 different monomers, as we've seen before, then for example we use something like nylon XY. So X is the number of carbons in the diamine, so that's the first bit. Remember that was 610, so that was the number in the diamine. Okay, and Y is the number of carbons in the dicarboxylic acid, which is there, that's 610. Okay, so it's always that way around, so just be aware. So whatever that first number is the amount in the diamine, the second number is the amount in the dicarboxylic acid. In one type of monomer like this here, really straightforward, it's just the number of carbons in that monomer. So this is nylon 6 because it has 6 carbons in this monomer unit here. Okay, so it's a lot more straightforward. Okay, so let's look at the other type of condensation polymer, which are polyesters. Now, we've seen, obviously, polyamides, so we're going to kind of build on this and look at polyesters. So polyesters are formed by reacting dicarboxylic acids and diols together. Remember, to form an ester, you react a carboxylic acid and an alcohol, and that forms your ester. So ester links are formed when we react these together, and so let's have a look. So there's our dicarboxylic acid, which is there on the left there, and then we also have our diol, which is there. So we're just reacting these together, and then what will form is our polyester, and there is our ester link in the middle. Okay, so very similar to the amide, except we have an ester. So we have the C classic ester link, C double bond O with an O bonded to it as well. And of course, because this is condensation polymerization, water is also eliminated from this reaction. So just as it is for polyamides, similar type of reaction. So let's have a look at an example of a polyester. An example is terylene. So terylene is a polyester that is used in plastic drinks bottles, sheeting, clothes, etc. So you might see it if you look on the bottom of a soft drinks bottle. You'll see the letters PET next to it. So if it has PET next to it, that means that it's made from terylene. Okay, so you kind of get an idea. It's a little bit more tangible. You know what terylene looks like. So it's made from benzene 1,4-dicarboxylic acid, okay, and it's made from ethane 1,2-diol. So let's have a look here. So there is our benzene 1,4-dicarboxylic acid. So that's it there. And this is going to react with ethane 1,2-diol. Okay, so we've got the 2 alcohol groups either side there. So these are going to react together and they're going to form our terylene, which is that, and water. Be prepared in the exam to be given 2 monomer units like this, and you need to be able to join them together to form your ester and repeat unit here. Okay, so just be prepared to do that. It's really, really important. And obviously make sure that you're eliminating 2 waters, because you're eliminating water in the middle here, but also on the edges of the repeat unit as well. Okay, so now we're going to look at, because we looked at hydrolysis of amides, we looked at hydrolysis of esters, we can also do hydrolysis of polymers as well. Okay, so condensation polymers can be hydrolyzed. Remember, you're going to be sick of me saying this, but hydrolysis is hydro using water, lysis is to break, so split using water. And if we hydrolyze a polymer, we actually get the original monomer units that made that up in the first place. And effectively, hydrolysis is just the complete opposite of polymerization that we've seen just before there. Okay, so let's have a look. So here we've got our polyamide. Okay. And we're going to add two molecules. Okay, so we've got our polyamide here. There it is. We're going to add 2 molecules of water because it's hydrolysis. And so once we do that, then we form our 2 monomer units that made it up. Because it's an amide, we form a dicarboxylic acid and an amine. Okay, so to determine the monomer units produced, we just break the bond in the middle of the amide or ester link in the repeat unit. So we just break that, and then we add OH and H to each of the monomer units. So you can see here we've got our OHs on the end here, and the H's on the end of your diamine. Okay, so remember, for polyester, we must produce a dicarboxylic acid and a diol, and for polyamide, we must produce a dicarboxylic acid and a diamine. Okay, really, really important. Just look at it. It's really straightforward when you look at it, actually. It's not too difficult. So it's just finding that link and deciding what monomer units are actually going to be produced. So like I say, we can work out the monomer from the polymer chain, as we've just seen there before. Now, what we do, again, I'm just going to quickly go through this because you've just seen pretty much an example there before, but this is just dedicated to the actual discovery of the monomer. So the monomer unit can be determined by finding the repeat unit. Okay, so what we're looking for in that polymer chain is we're looking for either an amide link or an ester link. We're looking for that link there. And then what we're going to do is we're going to take that ester link there and we're going to break it straight down the middle. Okay, there. So we're looking for that repeat unit. So when you're given a big long polymer chain, look for a pattern. Look for a pattern of repeat unit. Okay, we then break the link in between, which is here. Okay, and the monomer, just as we've seen before, we add hydrogen and OH to each of the molecules there. Okay, and then we form our monomer units, which in this case will be a dicarboxylic acid and a diol. Okay, because this is an ester link that's being broken. Okay, so condensation polymers can be more complicated, though. They can contain amide and ester links, which is just when you thought you got the hang of it. We add an extra layer of complexity in this. So molecules with amine and alcohol groups can react with dicarboxylic acids to form a lot more complicated condensation polymers. So let's just have a look at an example. It's always better looking at examples of these. So you can see here we've got our dicarboxylic acid there at the top, which is fine. But on the bottom here, we have an amine and an alcohol group at the end here. Okay, so instead of having a diol or a diamine, we've actually got a molecule with 2 functional groups in there, which is going to make it a little bit more complicated. So this is going to form something like this. Okay, so you've got your dicarboxylic acid. I've color-coded it so you can see what's going on. And we have our NH group here. So obviously one of the hydrogens has been lost, as is one of the OH, so that forms water. And then obviously you've got your oxygen here, which has lost the hydrogen. That's from this bit here. So you can see that we have our amide link in the middle. There it is. Okay, and effectively the ester link appears at the end of the repeat units. You can see there. So you've got C double bond O and O as well. So just make sure that you're drawing these correctly. Okay, they are a little bit more complicated, these examples, but just make sure you're being meticulous with what you're looking for. So it must be laid out like that. Okay, so condensation polymers, they can be formed from one type of monomer as well in some cases, so we don't need 2 different types. So, for example, you'd seen an example with nylon 6, that was using one type of monomer. But molecules with a carboxylic acid and either an alcohol or an amine group, they can actually react with itself to form a more complicated condensation polymer, just like nylon 6, as we've seen there. So, there we are. There's the one monomer unit, or the single monomer unit there. And basically this will react. You have loads of these in a beaker. These will react and form a chain to form an amide link in this case, because we've got an amine group at the end. Okay. And you can see the key thing here is there's a lot of kind of, I suppose, repetition with some of this, because you need to know the example of nylon 6, but nylon 6 is just one monomer unit that kind of bonds with itself. This is just showing you generically condensation reaction that one monomer unit can join to itself and form that long polymer chain there. Okay. Right, so just to kind of finalize this video, we're just going to look at some of the polymer types and just compare them, because we've seen a few different polymer types there. So just to kind of summarize this, so you need to know the differences between condensation polymerization and addition polymerization that you've just seen there. So the first one is the monomer unit. So in condensation polymerization, you must have two functional groups, a diol, a dicarboxylic acid, to form your esters, your polyesters, or to form polyamides, you need a diamine and a dicarboxylic acid, or to form proteins, which we'll see later on in year 2 if you haven't done it yet. Amino acids are then used to form proteins. Addition polymers are much more straightforward. They only use alkenes, and that double bond opens up to form your repeat unit. Okay, reactivity, condensation polymers. These can be hydrolyzed under acidic and basic conditions to break that polymer up into its constituent monomer units. Your addition polymers are unreactive. Remember, these are the ones which are not great for going into landfill, because they will sit there for years and years and years. They're unreactive. They don't have any polar bonds. It's really difficult to break these types of polymers down. Okay, and then finally, polymer formation. So condensation polymers are formed by joining two monomers together, and water is eliminated from condensation polymers, so that's emitted from the molecule. Whereas with addition polymers, the double bond actually opens up to form your polymer unit. Nothing is actually eliminated with that. So effectively, we're adding polymer units, adding the monomer units together to form your polymer. So that's why we call it an addition reaction. Okay, and that's it. That was quite a large amount of information. There's a lot in this one. It's a big topic, polymers in life. But that's the end of this video on organic reactions, functional groups, polymers, and isomerism. There is a full range of Salters videos for the year 1 and year 2 chemistry. Just go and have a look on Allery Chemistry YouTube channel. There's some generic whiteboard videos there. It's all for free. All I ask is you hit the subscribe button. That'd be absolutely fantastic. And just remember, if you would like a copy of these slides here, just click on the link in the description box below, and you'll be able to get a hold of them there. They're great value for money. All right, okay, that's it. Bye bye.